Well, here we are once again. This is Natural Science 116, the Natural Science 116 video lecture 7. And today we're talking about electricity and magnetism. And I'm going to start with the electricity review and then continue on where we had left off. Good, so electricity review. Okay. Electricity. So the first thing we have is static electricity. So there are some interesting phenomena that go with that. And what we learn is that it comes in positive and negative variety, positive and negative charge. There is an interaction, which means there's a force law between them, and the interaction law is that positive and positive repel, negative and negative repel. That is, like charges repel, but unlike charges attract. So, like charges repel, unlike charges attract. Okay. So when we say interaction, we of course mean force. We can feel some little force of attraction and repulsion. And so the next thing we can talk about is when we have charge separation. So since we have a force law, actually this isn't division, so I'm just going to leave it like that, interaction, force. So we have immediately we obtain an energy idea here, because we know that energy, and I always write W here, or I usually do work, force times displacement. Okay, so when we have charge separation, then that's what we're looking at. So I drew that picture last time. I just gave us the idea of some positives on one side, some negatives on the other, and we pull them apart. That takes work because it's an attractive force, and therefore we actually have energy stored in a configuration like this. You have separated charges, that represents energy, it represents work because of force times displacement. So here, and let's say we have positive Q on one side and negative Q on the other, we could say that this energy is Q delta V, and now we've introduced the idea that we've got charge times voltage. So for the charge, the unit was the coulomb, and then this delta V, the delta even represents a separation, so it's a good symbol. We always have the delta along with the V, and it as the unit of the volt. That could just be capital C, that could just be capital V. So there is our energy stored and ready to use. Okay, so what next? What's next is I'm going to show a demonstration. We have a Van de Graaff generator. I told you guys to go look it up, but we actually have one here functioning. Makes impressive sparks, so that's what we're going to do here. And it's even been labeled. Although we don't have to worry that much. As long as the charges are separated, we're seeing what, plus minus? Minus plus, yeah, good. So here's the idea. This thing is going to separate some electrons onto this sphere, and we're going to have a charge separation, and we're going to get some sparks. So let's get this thing going and see what happens. I'm going to put about this close together. Lights off, and get some sparks. be visible on camera. I think I break that out a minute ago. So we have a discharge from one side to the other, definitely visible. And that's what we wanted to see. Okay. So there's an illustration, but we've also seen the next idea in the progression here. Namely, so we'll put here demo Van de Graaff generator. Okay, well, what we saw there, that spark was actually showing that there was a current. Namely, there was charge going from one sphere to the other. So current, electrical current, it's the letter I, is charge per unit time. Charge per time, so the units are clearly coulombs per seconds. Okay, so we've got an electrical current, coulombs per seconds, and that is the ampere. Amps, we'll talk about that, just capital A for amps. Okay, so what do we have? We had stored energy. In fact, you could have said there was stored energy here and then it was released with that current. So current has to be here in the mix. Is current here? Not yet. But we see the Q there. And let me give a couple more examples of current before we continue on here. So examples, the one we just saw, electrical discharge. You know, we had the minus, we had the plus, and we had that lightning, okay? Another one that you probably would have thought beforehand would be the current in a wire. So I'm going to write in a conductor, we're talking about electrical conductor, often but not always a wire. So in that case, you can almost think it's like water flowing through a pipe, except with the electrical current there, the actual transport of mass is negligible. Okay, the electrons are so low in mass that when they're moving through and on the surface of a conductor, it's just not really a transport of mass. Nonetheless, we can imagine there's a bunch of electrons here, and they are flowing. Okay, so there's a current, and its Q per time would be Q that would be passing a certain cross-sectional area in a certain amount of time. Okay, so there's your electrical current, and now we want to make contact with this concept here, as we saw last time. Okay, let's go ahead and set this up. So I'm going to erase this and use this formula again. Okay, so we've got the electrons flowing in the wire as an example of the current. And now we get to power. I had this up on the board last time. Power is work per unit time. Good, but we have an expression for work here. Here in the electrical world, we have power, work over time is Q over T delta V. And I drew your attention last time to the fact that this is just like our hydropower formula. So I'm going to put here, recall hydropower. There we had P was M over T Okay, so now we have Q over T. It's not mass transport, it's charge over time, delta V. And so we can see the potential difference is what this delta V is called, corresponds to the elevation difference. Okay, we even refer to this as a potential drop, corresponds to the elevation difference in hydropower. This is the reason we're able to make such rapid progress here in electricity. Generally, it takes a while to get to these concepts, but we've studied power and, earlier on in mechanics, and now we're ready just to take over those concepts here in electricity. So what was our power formula? P was equal to pi delta V, something you'll never forget. Watts is amps times volts. Very useful to know even in the household world. Okay, I'll put it here, watts equals amps times volts. And then I had given some homework on exactly this formula. So this is one that we're going to want to be able to work with in the coming week or two. And of course on the final exam. Yeah, that's about as far as we had gotten last time, so we want to keep going with this and go into the circuitry. So far so good. Okay, let me sum this up. Now we'll go into the circuitry in a little more detail than we did last time. I really have one basic circuit in mind that we're going to analyze and discuss and get quite a bit of results out of it. Okay. So what do we have? We have power, we have current, we have voltage. So let's go ahead and draw a circuit. I'm going to do the literal model. This is worth talking about. So this time we'll hook it up to our car battery. Got a plus and a minus. Everybody's seen their car battery before. And we'll take wire to a light bulb of the kind of the little shell here. And if you look closely at the light bulb, you'll see there's a little filament inside. And that filament is actually the continuation of, here I'm going to use colors, continuation of this wire here. And I'll even use red to indicate that it is glowing. It's a very thin wire. And then that comes to here. Okay, so we've got the current coming in here, out there, into the terminal. So there's our circuit. What we have is a continuous flow of electrons, a current going around here. Why does the bulb glow? It glows because that filament is literally red or even white hot. It's really just heat, and the heat at those, the metal at that high temperature actually gives off visible light, and that's what we're seeing. If you grab this bulb, you're going to burn yourself. It's very hot, so it's giving off heat as well. Okay, very important. And because it's radiating light and heat, we can definitely say there's power being used. Okay, so there's our power formula right there. This battery has some voltage. Car batteries, 12, D-cell, 1.5, different batteries, different voltages. Okay, and there's a current here, and we did those numerical exercises last time. You just use this formula, and you can solve for one of the unknowns. Okay, schematically, what does this thing look like? There is a battery, there is a wire, there is what we call a resistor or a resistance. Okay, same thing, we have current, we have delta V, except we have to discuss what this resistance is, because up until now we've just known that there's power. But the resistance has something to do with the power. We can think of the resistance as a friction, something that's resisting the flow of the current. In the light bulb, it's because that filament is so very, very thin that it gets so hot. So the filament has a lot of resistance here. So it produces heat. So we have a second law that we have to talk about. We've got the power law. So I'm going to write here next. We have Ohm's law. And that relates the voltage, resistance, and the current. Delta V is equal to R times I. Okay, so this is one we're also going to have to know. What are the units of R? Well, they're the units volts divided by amps, and that is called the ohm. And it gets this capital omega, uppercase omega, as its symbol. But yeah, voltage, resistance times current. Okay, so these are one and the same circuit. So apparently it's a resistor that gets hot, and in this case radiates heat and light. So resistors get hot, which is to say resistors actually are the place in this circuit where the power is dissipated. Okay, we can do some numerical examples of this. I think I'll come up with some at the end of the lecture. We'll make a little list of problems we can do, because we're just going to have a handful of formulas. Okay, so we've got the delta V equal Ri. We have P equals I delta V. So we can combine these two, 1 and 2. We can combine them and get one more useful formula. P is equal to I. And now for the delta V, I'm going to plug in the R times I. And now you see I have I squared. So that's I squared R. I'll put that down here alone and in a box. I squared R. Now this has some significance for the practical discussion. In principle, we only need these two because this is just a direct corollary. But for the practical discussion, this is important. Namely, the power for a given resistance, say for a given light bulb or something, increases quadratically in the current. So if you double the current, you have 4 times the power. You triple the current, you have 9 times the power. Now here's the practical concern. In my picture here, the only thing getting hot is the filament. So we have this idealization in electricity where we treat the wire that's going to and from the light bulb, we treat it as though it had no resistance and therefore generated no heat. Okay, but in fact, these wires can also get hot. Okay, in real life, these wires will definitely be able to get hot. And you can see if you don't want them to get too hot, you have to keep the current sufficiently low. Okay, if for some reason the current doubles, triples, quadruples, not only is your light bulb going to be hot, but your wires will start getting hot as well. And these wires are in the wall. And if they get too hot, your house will burn down. That's the idea. That's the idea behind circuit breakers and fuses and stuff. Good, so that's why I had to bring that up. And I'll put that as a note. We've got the quadratic dependence. Quadratic dependence on current. Okay, that's really the set of formulas that we need here in the electricity world. We first have the definitions, of course. We have to know about our coulombs and seconds and volts, then we have the power formula, and we have Ohm's law, and we have this corollary here. Okay, so let's look at a couple of examples. of where power is being used. We're using the light bulb as an example. Really anything in your household that's just generating heat using electricity is the subject of these laws right here. That would be the coil in your hair dryer, your curling iron generates heat, your range top generates heat. The coils in a space heater, you actually see them get glow orange, they're generating heat. They're all a version of this circuit right here. Okay. So I want to give one example of this. So let's call this example, don't know what numbers I have going right now. So this example, energy or power and energy. So of course we know we have the power equals energy over time formula, and therefore we know that power times time, just cross multiplying, is equal to energy. Good. What kind of energy? We're talking about thermal energy because heat is being produced. Okay. So power times time gives us this thermal energy, and as an example, I'm going to write heat energy. Good thing I'm using the capital Q for the heat and the lowercase q for the electricity, okay? So I'm talking about energy in the terms of heat, and we had a good formula for that. Mass, specific heat, change in temperature. So this is an example that we can use for a lot of things. What would the units be here? Joules. What would they be here? Watts times seconds is joules, but we could also convert to kilowatt hours. Okay. So if we're heating something up, there's our circuit, maybe we're boiling water with using electricity, then the amount of energy that we're interested in is how many kilowatt hours is, because we're going to convert that to dollars and cents. So this is a good formula here to do some homework problems on. Power times time, that's energy. If it's thermal energy, then we have the MC delta T formula from heating things up. Okay, remember, specific heat of water was 4,186 joules per kilogram degrees Celsius. Yeah, so let's go ahead and write down an example problem. How many joules or joules and joules, comma, kilowatt hours, one way, the other way, required to heat 10 liters of water from 20 degrees Celsius to 100 degrees Celsius. That's a good problem. I could put that on the homework. I could do it right here. How about we call that homework? So go ahead and do that and turn it in with your notes, but we'll get started on it together, okay? So the formula is actually written up here already. If we want to know how many joules, we'll just put in the 10 liters. Did I say 10 liters? Yes, 10 kilograms. Remember, a liter has a mass of a kilogram. So we'll put in 10 kilograms, you'll put in specific heat of water, and the delta T will be 100 minus 20 will be 80. So that's just going to give you a big number. Okay. It's going to give a big number. And what did we know about the kilowatt hour? We had 1 kilowatt hour was 3.6 times 10 to the 6 joules. Right, the joules don't tell us much. The kilowatt hours, we know how much we're paying for them, 25 cents or whatever. Check your bill. Check your electrical bill. So yeah, that's how to do this, and we should be able to do any number of problems of that type. The other interesting problem is, how long does it take to heat this water. So how much time is required? Question mark. Question mark here too. Okay, how much time is required to heat that water? Again, the formula's up here already. We have to know what the power was. So how much time is required, comma, if power equals, what's a good power for something like this? 1,000 watts actually, 1,000 watts. Okay, so you've got a 1,000 watt burner, say, on your stove. Then we have this number, let's just say the Q, we have the power, now we just have to solve for that time. And the time will be in seconds, okay? If you're talking about the joules, then the time will be in seconds. So that's, yeah, it's a practical type of problem, and it's really the same thing we've done before in hydropower, which is why that was good to bring up. So that's basically the set of skills we want to have for this part of the electricity. This is the whole household electrical power aspect. I talked about circuit breakers last time and circuits, so if we combine that with what we have here, we're pretty much complete in these practical applications. We can scale it up for how much power the whole civilization needs. Good, let's see how we're doing for time here. Okay, we could maybe condense all of this onto one board one more time, and then I want to get into electricity and magnetism specifically. Yeah, okay, so I'm going to set this up, and I'll gather all of these things in one board. On one board, maybe add a few problems to the mix. Okay, so I'll just call this electricity and get the condensed form. Okay, so we have charge Q Coulomb comes in positive and negative. We have electrical current, I equals Q over T. That's the ampere. Okay. Then we have energy, Q delta V. And the delta V is the voltage. And with those ingredients, we have power equals I delta V. We have Ohm's law. Delta V equals R times I. Okay. And then everything else we do using the mechanics concepts that we've already learned. Power, work, time, and so forth. So, I will add to this, we have our circuit. And the real version, I like to draw with the battery here. That is, the actual object, the light bulb. All of these things we're doing, if there's thermal heat, if thermal physics involved, it's just like the light bulb. there's the current, there's the delta V, there's the power, and if we do the schematic diagram, there's the delta V, there's the current, there's the resistance, there it is, it's all there in a nutshell. And energy, power times time, as an example, MC delta T. And that ties us right into our thermal physics type of problems. Yeah, so these are the things we want to be able to work with. There's a homework problem right there, which is a nice one. And let's add a bit more to this. So we've got the power and the time, so that's a good question right there. So if R equals 6 ohms, delta V equals 12 volts, find I and P. Okay. Good. And you know, I'll put on this list here, it's just to look at the examples we had. So check examples from lecture number 6 and make sure you understand those as well. From lecture number 6. And there it is, all on one board, our electricity discussion. The need for circuit breakers I talked about, if the current gets too high, the wires get hot, so really we have a good discussion. This example here is going to be very important. We're going to see it again when we talk about solar energy of all things. So yeah, definitely understand and do this one right here. Good, so let's set this up and kind of outline where we're going next. You'll notice that I haven't mentioned motors yet, and I've really just restricted this to batteries. Although last time I said the formalism does work for the alternating current, but we haven't gotten to the alternating current yet. So in order to have large-scale use of electricity in civilization, we have to go beyond the battery, okay? And in order to go beyond the battery, we have to know about electricity and magnetism. So that's going to take a little bit of setting up. And of course, we've got this countdown to the end of the semester that's on our mind. How much are we going to be able to do? Well, we're going to do enough. Okay, there's good ways to deliver this in a condensed form. So in fact, what we're going to do is just talk about the laws of magnetism and electricity in the very fundamental sense. Namely, just bring some magnets here, talk about them a bit. The relation between electricity and magnetism is what allows us to get motors, transformers, everything else that really runs things on a large scale. So the next set of topics is just electricity and magnetism. And in particular, I have to bring some magnets out. Then we'll, after we look at these separately, then we'll see the relation between the two, and then we'll be able to move on. So as far as the electricity goes, we've talked about it. There's one more thing I have to note is the electric field. And we didn't really need it in this discussion up here. I'm going to make that up by first talking about the magnetic field and then relating back to the electric field. Okay, so we're definitely going to get started with the magnets now and the magnetic field. That'll be nicely illustrated. So we need magnets. So simple magnets. Everyone's got one on their refrigerator. And I brought a couple of magnets here as well. So, get a box with a few different magnets in it. And basically what I'm going to show is some version of the bar magnet. I've got a bar magnet here. What I want to show is go. So here's a short bar magnet, here's a longer bar magnet. It's made out of segments, but there's a point behind that. So if you've held magnets before, you know they attract or they repel, and you can actually feel those repulsive forces. Kind of interesting because they're not touching, and then they attract and stick together. So we've got a north and a south pole here, that's what we say. Okay, and we'll say that the opposite poles attract and the like poles repel. Okay, so if I get a repulsion here with this blue side, I go to the other end and I'm getting the attraction. Okay, if I get the attraction with the red on this side, I go to the other end and get the repulsion. Okay, so this is a bar magnet. The interesting thing though is I can break it in half. You know, I have two bar magnets. Now, did I end up with a north pole in one hand and a south pole in the other? I did not. Because again, this will have an attractive side and a repulsive side. I could actually push these around as demonstration. Or I can get the attractive side where they stick together. And I can keep doing that. I can break this magnet and break this magnet. And this will still have the same properties as the entire magnet did before. Okay, the repulsion, turn it around, attraction. So what that shows is you can't isolate a north and a south pole. If I were to slice this thing in half, it would still have its north and south pole. I slice it in half again, it would still have its north and south pole. So those are things you've probably done before to some degree, and we're just going to write them on the board. Yeah, magnets like to jump around here. Good. So we're talking about magnets, and the first thing is we'll draw a bar magnet, north and south pole. So north and south pole, and we have like poles repel, unlike poles attract. That kind of reminds us of the charge. The difference is we cannot isolate a magnetic pole. No matter how small you cut those things, they're always going to have a north and a south pole. That has some important ramifications. Cannot isolate a magnetic pole. By the way, why are they called north and south pole? If you take a magnet like that and suspend it from a thread, it will point to the magnetic north. Okay? That's why it's called the North Pole and the South Pole. And yeah, leave it at that. So I've mentioned the compass needles, and this will bring me to a discussion of the magnetic field. So the magnetic field, bring in this big old magnet right here. Hoping it's in the field of view. This is a big magnet. The first thing I want to show, this one's kind of fun to have around. It's very powerful. So the north and south pole facing each other, and if you throw metal at it, it catches it. Okay, so that is not a weak magnet. It's a pretty strong one. Now, there's an influence out here. We're going to talk about the magnetic field. What is this field idea? There's an influence out here. I can feel it if I take a test object. Like I said, it seems pretty tenacious. And I have, here's an interesting demonstration. There's an array of compass needles here. Okay? An array of compass needles. Are we in front of the camera? Let's make sure we're in front. And you can see that these compass needles move as I move around here. In particular, if you look at any single needle and follow it, it does a full 360 degrees as I go around here. If I hold this thing up higher, you can see the curvature that the needles assume is a little smaller here, curving greater. So actually these needles are lining up along what we call field lines. An equivalent demonstration is if you have a bar magnet and you sprinkle iron filings around it. I'm going to put that on the board. You guys can either do it or look it up, get some images. So yeah, you're going to want to get some images for magnets and magnetic fields. Very interesting topic. Here, seeing these compass needles move is pretty interesting in its own right. Okay, wheel this object back off. Yeah, so we want to talk about this magnetic field. So what do we have so far? Bar magnet. No matter if I were to break this in half, quarter, eighth, it would always still have a north and south pole. And I just showed you how these compass needles arrange themselves when I hold them near a big magnet like this. So that's what we're going to talk about next. Okay. So this next picture is called the magnetic field. So next, the magnetic field. And I'm going to say I already demonstrated it. The demonstration with the iron filings is not going to be done today. But you'll recognize what I'm about to draw. So if I drop iron filings or compass needles, they all have some sort of a direction. Let me draw the field lines first. So for a magnet like this, we get field lines leaving the North Pole and going towards the South Pole. So if you have, okay, so what do these field lines mean? When I had little compass needles here, they were arranged like this. That's why when I held the array of compass needles, the ones I'm drawing in red are kind of the ones that you saw, okay? And when I brought them out to here, we saw these directions. Okay, so that's the way the compass needles align themselves. And if you join those lines, implicitly defined lines, you get the field lines, and that maps out the magnetic field. So that's the generic form of the magnetic field. Again, if you have a bar magnet and you put a plate of glass over it, you can sprinkle iron filings on it, and the iron filings will assume this configuration as well. So let's put this as a note for you to look up. Magnet and iron filings. And another thing you can look up is just magnetic field. You'll get some good images for your book. And hopefully something that goes along with exactly what I've shown you here, the magnetic field. So you've got the attraction, the repulsion, these interesting properties, and you can make them visible by doing what I just did, the compass needles with the iron filings. Yeah, so get some images of these things. And now I want to go to the electric field. So what about the electric field? fact, here's what I'm going to do. I'm going to start a new board here and compare the two. Direct comparison, because now that we have the magnetic field, we'll have some idea what we're thinking of. Okay. So we've got the magnetic field on this side, the electric field on this side. This one we call E, and it's a vector, and this one we're going to call B, and it's a vector. So over here I'm just reproducing what I had there. North, south, I've got what's called the dipole field. Okay. So this is called the dipole field. In fact, go ahead and look up dipole field as well. D-I-P-O-L-E field. Go ahead and look this up. Now, the nature of the magnetic field is really connected with the fact that you can never separate a north and south pole. The electric field, on the other hand, you can separate a plus and a minus charge. Okay. You can literally separate them. This field will be radially outward. Let's make that radially outward. It will be radially outward, and this field will be towards. Same with the opposite direction. And these are assumed to be separated. Okay. So we say the electric field actually has a source. The charge is the source of the electric field. Of the E field. The magnetic field is a little different in those regards. Okay. Good. So how would we already see how to visualize the magnetic field? To see the electric field, you'd have to do something different. You could take the Van de Graaff generator. You've seen pictures of this, and maybe you'll look them up and do that as well. And then some girl with really long hair has the hands here, and the hair is standing out like that. Okay, no chance of that happening here today. But if you look at images, Van de Graaff generator and electric field, you get an idea of precisely this. Okay. Good. So I've introduced some principal facts and properties of these magnets, of magnetism and electricity. And for next time, we're going to get the laws of electricity and magnetism. As my final section on this board here. So next time, the laws of electricity and magnetism. You could say we've already started with laws of electricity because we learned about circuits and power and energy. When I talk about the laws of electricity and magnetism, we're going to find relations between electricity and magnetism. So we're going to find relations between E and B for shorthand. And these are going to be crucial in order to find out why we can generate electricity, why we can have motors, why we can have transformers. So relations between E and B, comma, and then we'll also talk about generators, motors, transformers. And like I said the other day, eventually on our last day of review, we'll probably make a giant cartoon with everything that we had and try to show how they're all connected. Okay, so that's enough for today. Make sure you take good notes and take note of what we thought of as good homework problems. Also, the images that I recommended, you can get some nice printouts for your book as we've been doing. Okay, see you next time.